Good afternoon and welcome to today's webinar, Thermal Imaging Cameras, Applications in the Utility and Energy Industries. My name is Paul Kusker from Transcat, and I'll be your moderator this afternoon. Joining us on the call today is Ed Kahanek, Eastern Regional Sales Director from FLIR, who will be leading us through today's webinar. If you do have questions from this webinar, we will give you contact information at the end of the webinar, so feel free to reach out to us with any questions that arise from the presentation. We will spend today's first part of this in presentation mode, and then we will do a little quick wrap-up. At this time, I'm going to turn over the presentation to Ed.
Thank you, Paul, and good afternoon, everybody. My name is Ed Kahanek, and I work for FLIR. I will be giving a presentation on thermal imaging cameras and their applications in the utility and energy industries. Partnering with FLIR is Transcat. Transcat is a distributor of any type of test and measurement instrument you would need, such as a spot temperature gun and or thermal cameras. I'd like to start off with a challenge to you. You aren't doing everything you can to prevent unscheduled downtime. I know this is a bold statement. Thermal imaging has come a long way since the days of $50,000 infrared cameras. Today's cameras are very affordable and much easier to use, eliminating many of the hurdles to purchasing, such as price and complexity. There are hundreds of applications within every company, and hopefully at the end of the presentation, you will gain an appreciation of what a thermal camera can do for you. Here is the agenda of what we will discuss to show you how you can tackle unscheduled downtime and what it means for your organization. First, we will discuss applications for your industries. We will also discuss return on investment. And finally, which camera is right for you. The reason for the clock in this picture is to talk about time being the most frequent measurement people make every single day. The number 2 most frequently measured value is temperature. So why is temperature so important, and why would it be a benefit to see temperature? Every day you walk around your work environment wondering when the next problem will happen or what will fail next. Without the proper tools, it's impossible to detect these pending problems. Generally, our human senses are unable to detect the clues to these potential failures. However, industrial equipment does give off one major clue. When equipment goes bad, it generally heats up. Mechanically, because of friction. Electrically, because of resistance. All these targets get hot prior to failure. And wouldn't it be nice to see that? A change in temperature or a difference between two similar components can show a problem. In this picture, this person has an injured arm. The body is working to heal itself, and the additional blood flow and inflammation makes that area of the body heat up close to the core temperature. However, the difference between a human and a piece of equipment is that a human will tell you where and how it hurts. We are not so fortunate with our industrial equipment. As we can see in this picture, this individual's left arm is much warmer than his right arm, indicating what he already knows is that it's been broken. To try and measure temperature, industry has relied on the spot temperature gun instrument. The reasons are pretty clear. The spot gun is affordable, easy to use, and gives you a temperature measurement wherever you point it. However, does the spot gun tell you everything? Does the spot find all your problems? Does it measure accurately? The answer to all these questions is no. The spot gun is a poor temperature measurement tool compared to a thermal imager. And for full disclosure, FLIR is the manufacturer of one of these brands on this page, so we know what we're talking about. Thermal cameras have generally been considered too expensive and too technical for your average maintenance technician. In fact, the major use of the thermal imager has been in the electrical room or service of your industrial plant. This is usually where your most expensive equipment is located and what can do the most damage if it failed. However, as you go to this part of the plant, you pass by all the other potential applications that you can use the thermal imager on. Since the equipment you walk by will have its own unique temperature scan, when healthy or sick, you should scan these too. And in this picture, we're showing pictures of roofing, energy, bearings, motors, bus ducts, tanks, belts. All of these are potential applications that a thermal imager can help you solve the problems that plague the plant every single day. So what's changed? Why the move to thermal imagers? Cameras are more affordable now than ever before, with entry-level cameras starting under $1,000. Cameras are easier to use with point-and-shoot capabilities. Cameras are now rugged with 6.5-foot drop test ratings. Cameras have adopted smartphone technologies with touch screens and Wi-Fi capabilities. All these features have led to the mass adoption of this technology throughout the utility and energy industries. A thermal camera uses similar technology to the spot temperature gun. It measures the signal strength of the infrared radiation from the target. A spot temp gun has one sensor. The benefit of the thermal imager is that it could potentially have thousands of sensors, as in the case of the FLIR i7. The FLIR i7 has a 140 by 140 pixel array, giving it 19,000 measurement sensors, as you can see by the grid on this picture. Each one of those pixels can give you an accurate temperature measurement. To match the thermal camera, you would need 19,600 spot guns arrayed together to get the same data. This is obviously not practical. The thermal camera also produces a two-dimensional picture where each pixel can be read for its exact temperature measurement. This gives the camera operator a clear understanding of how their equipment is performing. The thermal camera also does this very fast and usually from a safe working distance. A picture's worth 1,000 words has never meant as much as it does now. So let's look at our first example. We saw this picture in the visual picture montage earlier. At the moment, our eyes do not tell us that anything is wrong with this switch disconnect. When I use the thermal camera, I can clearly see that B phase is warmer than A and C. Since B phase is warmer, this is a good indication that there is a problem at this connection. It is probably loose. By seeing this problem with the thermal camera, you now have the ability to fix it before it fails. By measuring the temperature, you also have the ability to predict when it will fail, as this will give you the ability to schedule the repair at your most convenient time. Being able to predict when something will fail will allow you to make certain that the parts you need to fix it are on hand and have been ordered without any sense of urgency. Another application with utility poles is the transformers attached to them. When I look at these pole transformers, I'm expecting them to be a uniform temperature. The one on the left has a unique pattern indicating a major problem. We can see that the problem is caused by low oil, as we can see the oil level in the transformer. We have all lived through the consequences of a transformer failure. The area it services gets a blackout, causing potential problems for the residences or facilities it serves. With regards to facilities, it could be business interruption costs. With regards to residents, it could put people in an unsafe environment. In the picture, the arrow is indicating where the low oil is. Inside a substation, there are many targets to look at with a thermal camera. For example, in this picture, we see three separate problems. The first problem is the oil-filled circuit breaker. We can see the center one is warmer than the other two tanks. They should all be the same temperature. Since the oil acts like an insulator, the object inside has to be really hot to warm up the oil this much. There is a lot of oil in these tanks, and it takes a lot of energy for the camera to measure about 30 degrees warmer from one tank to the other. If you look above the oil flow circuit breaker, you'll see that there's a loose connection as well. A phase is warmer than B and C, indicating there's probably a loose connection there as well. And finally, above the transformer, we see another loose connection. This is one substation that was lucky enough to have someone come by with an infrared camera to locate all the potential problems. Here's a picture of another transformer. The left side is about 3 degrees warmer than the right side. The left side measures at about 119 degrees, with the right side measuring about 116 degrees. There is only a 3-degree rise, but over time this could get worse. Excessive heat will reduce the life cycle of a transformer, so discovering this issue will allow the utility to repair it when possible. In this case, the transformer had shifted, the pad had sunk on one side, allowing the oil to move to the other side and thereby reducing some of the oil flow in the high side. On this transformer, we can see that the oil level is below the radiator tubes. Therefore, the transformer is not getting the proper cooling. Oil is not flowing through the radiator tubes and therefore not cooling down and then not returning back to the bottom of the tank. This is another situation where over time, excessive heat will shorten the life of the transformer. The low tap changer in this picture should always be the same temperature or cooler than the transformer. As we can see in this picture, the low tap changer is much hotter, and that is a major concern. In fact, that low tap changer is about 17 degrees warmer than the transformer. One nice tool in the infrared camera is the Area Max box, and this tool on the camera allows you to quickly ascertain what the max temperature is. This makes it easy to find out how hot your target actually is. Here's another picture from the visual montage earlier. We can see that the fan motor in the lower right is not moving. The other fan in the upper left is moving by the indication that the fan blades are blurry. Here is the same picture in infrared. In this case, it's absolutely easier to see the problem thermally. By not cooling a transformer, it can have drastic results for the substation. When transformers fail, they cause major damage to all around them, especially if they explode. The premature loss of a transformer is a major problem for the utility. We will be discussing that later in a white paper given by one of our customers. As you know, transformers are not sitting on the shelf. It can take up to a year to get a replacement. The infrared camera can only see and measure the surface temperature of a target. We've discussed this in other applications such as the circuit breakers and transformers. However, the same is true when we have other indirect measurements, as we do in this case in the load break elbow getting warm. That's the one obviously in the upper left. The rubber boot acts like an insulator protecting the components inside. However, when one of these components gets hot, it takes a lot of energy to show up on the surface, as the rubber boot is thick. As we can see from the schematic, the load break elbow has many points inside the elbow that can get hot. Tests have shown that actual temperature rise could be 10 to 20 times greater at the problem inside the rubber boot. Therefore, on any indirect temperature measurement, proper identification and concern should happen every time you see this type of application. Here we will discuss another example of indirect temperature measurement. Using the thermal camera, the customer was able to find a 250-degree isolated temperature rise on the side of a transformer. After discovery, a repair was initiated, and this was found. The component was made out of aluminum, and you can see it was falling apart and melting. Aluminum melts at 220 degrees Fahrenheit, so you can imagine how hot it actually was. This temperature rise was approximately 6 times greater than what was seen on the outside of the compartment. This could have been a catastrophic problem if it went undiscovered. This brings us to the white paper I had mentioned earlier. You will be getting a copy of this white paper when we email this webinar to you. It's a story about how PG&E reaped the rewards of outfitting many of their maintenance and service people with thermal imaging cameras. PG&E, which stands for Pacific Gas and Electric, is a large utility in California that has been using IR for reliability for decades. But they saw the need to use the technology more broadly for their linemen and troublemen. In rolling out 350 cameras, they saw the benefits in safety, frequency of scans, business interruption prevention, broader coverage of components, and cost savings. In one case, an electrician found the failing transformer. In general, the cost for replacement could be anywhere between $1.8 and $8 million. In this case, it was $3 million. The radiator was clogged and there was no oil flow. The repairs were immediately scheduled, saving $2.7 million and taking in about 1/6 of the time to repair of what was versus installing a new transformer. This is a nice example of how thermal imaging program paid for itself with one find. As we transition, we will now look at some of the applications in the energy and chemical and industrial industries. There are a lot of applications here, a lot of electrical applications, which we described earlier. But in this part of the presentation, we will concentrate on some of the more mechanical applications or the unique applications that you could apply a thermal imaging camera to. In this example, we can see that one filter stands out from the others. We had talked earlier about looking for uniformity, what doesn't stick out. In this case, one of the filters is about 10 degrees warmer. The increased temperature was caused because the filter was clogged. This is not a target normally scanned by a thermal camera, but obviously one can benefit from. And the reliability engineer or the maintenance person was able to determine which one of these filters was actually having the problem. In this picture, we again see many components doing the same work. And by temperature differential, we're able to see which one is not on. It's the one in the middle. And the reason why we know that, it's because it's not creating any heat. That's right. Not everything fails because it's hot. Sometimes things don't turn on, and you can see that by their lack of heat. So thermal imagers are as good as finding targets that have a lack of heat as those that have too much. Therefore, the operator, by using the thermal camera, was able to quickly find the faulty transformer, get the repair going quickly. Here's a unique picture of two problems on a vacuum line. The first one shows a nice cold band, indicating a blockage from both top and bottom. We can see that as the vacuum is all yellow and there's this nice purple band right in the middle. The one right next to it has a nice band across the top of the vacuum line. So that appears to have a blockage at the bottom. Again, these are targets not usually associated with a thermal camera, but can greatly benefit from access to a thermal camera. Many industrial and energy plants have cooling towers. We see them everywhere. Here's a section of the tower that is warmer than the others. Not many technologies would be able to discover this problem. Thermal cameras in certain situations can see long distances. And finding issues on large-scale targets is much easier when you get a two-dimensional picture from any distance that can frame the picture. This gives you the ability to do comparisons. And in this case, we can see that there's some very warm panes on this cooling tower. Here's a picture of a worm gear. As we know, there are other technologies that are used to predict mechanical breakdown on motors, gearboxes, pumps, and bearings. Vibration analysis is one of them. The issue with vibration is that you need to physically touch every target to get a reading, and then you need to build a database of these readings for comparison. This can be very time-consuming. Therefore, the return on investment for vibration and other databasing technologies will be much longer versus a thermal camera. Thermal cameras give you instant feedback. On top of that, as we can see from this picture, the worm gear is elevated. We are looking underneath it, making direct contact very hard and not likely. Our industrial facilities and plants are chock full of applications like this, where in the past we would run them to failure because discovery would be difficult at best. But with the thermal imaging camera, being able to measure temperature and seeing the difference in temperature indicating a problem, that may no longer be the case. Here's a thermal picture of a motor with a distinguishable temperature mark from problems in the windings. In fact, there are three distinct marks. The arrow's pointing to the one at the top, there's one slightly to the right, and then there's one directly below it. Since these spots are small, a spot gun would have trouble finding them. As we have discussed earlier, spot guns have very small spot size ratios. Finding a winding problem motor is near impossible. And as we know, every industrial factory has many, many motors. Keeping them running is very important, and a thermal camera will make that much easier. We keep continually talking about comparison images, and this one is no different. The difference in temperature between these two objects is very clear and would not have picked up by a spot gun. Both motors are the same model doing the same exact work. And I have to emphasize, when you're looking at motors, when you're looking at bearings, when you're looking at gearboxes or pumps, you have to ensure that unless you have a database of these targets, you need to be looking at motors and gearboxes and bearings doing the same amount of work and being from the same manufacturer and being the same model. Because if they're not, you will not be getting the full value of what the camera can do. So in this case, we can clearly see that the motor in the background has a localized hotspots. And all motors have a thermal rating indicating how hot they can operate. This thermal rating is generally notated on the nameplate of the motor, and that corresponds to a temperature that inside the motor it can operate safely. However, if the outside temperature of that motor exceeds the thermal rating by 18 degrees, meaning that the inside is actually much hotter than the thermal rating it was designed to be, you can expect to cut the life cycle of that motor in half. If you exceed the thermal rating by 36 degrees on the outside, you have now cut the life cycle of that motor to a quarter of its expectation. Here's an example how a camera can quickly find a dangerous situation. The breaker is de-energized. The breaker is de-energized, but the CT is hot. The customer had already repaired this 3 times, but this was an ongoing problem. There was a loose and vibrating connection between the transformer and this connection that made the CT act as if there was current. This would never have been on the list for a normal IR survey because it was de-energized. But the fact that the electrician had a camera at that moment in time, he was able to discover the problem and finally fix it. As we discussed earlier, bearings are always a good target to consider for any thermal imager. In this example, we can see 2 bearings doing the same exact work. One bearing inside this motor is clearly warmer than the other. It's warmer to about 20 degrees. When the customer discovered this problem, they opened it up and noticed all the score marks on the bearing, as we can see on the picture on the left side. The right bearing, brand new out of the box, as we would expect, is nice and smooth. So once the customer replaced this thrust roller bearing, they were able to see, when they were able to use the camera for a checkup, to see that the operation turned back to normal. And the temperatures were all the same. So that is a nice picture and success of what a thermal camera can do, not only discovering the problem, but validating the repair. So I've shown you over the last 25 slides a number of examples of where a thermal camera can pay you back. As a camera manufacturer, we've always said the camera will pay for itself very quickly. We've heard stories about the cameras paying for itself the very first time it was used. While this is not always the situation, we do feel strongly about how quickly a payback you can get. Recently, one of FLIR's good customers wrote a paper on their use of thermal imaging and how it's improved their customers' bottom line. C&A is a major insurance company who writes loss prevention policies for many industrial customers. C&A conducts surveys of these companies' facilities to estimate the risk and reduce problem areas. C&A conducted a 5-year study on all their thermal surveys. Of the 6,000 IR surveys, they found 47,000 faults, 7.3 faults per survey. Their survey saved their customer $55 million in replacement costs. That is the cost to replace the product or the part that was about to fail. This works out to $8,500 per survey. As you can see, the average sale price of a thermal imaging camera is generally below $8,500. Therefore, you could pay back your camera within 1 year. What also is nice, and what also they found, was almost half of the surveys had one critical fault, greater than 75 degrees Fahrenheit. These are the problems that are most likely to fail catastrophically. The costs listed in the charts are based on C&A's insurance historical database for electrical fires from switches, circuit breakers, and motor control center. The average loss from an electrical fire is $750,000. If we factor in business interruption, and business interruption is the cost associated if the factory or the utility stops making the product that it sells, C&A factored in that this was $2.3 billion in loss prevention. That is a significant payback to American business. Again, as I stated, you'll be getting a copy of the paper by C&A, and you'll be getting a copy of the paper by PG&E and how they use their technology, this thermal imaging technology, to save money. So that ends our discussion on applications and payback. I thought it'd be nice to start here and have a brief introduction to the infrared cameras that FLIR offers. When reviewing your camera needs, you should consider a number of questions. First question is, how far from the target am I? Basically, this applies to the resolution that you would need. There are many different types of cameras out there with many different types of resolution. How hot is the target? FLIR makes cameras that go up to 2,000 degrees C. You may not need all of this temperature range, but we do have cameras that go up to this temperature range in various stages. What other applications are you looking at? Some of FLIR cameras have very high performance values such as refresh rate, how fast you need to take a picture, and do you need to connect it to a computer? How often will you use the camera? Will it be daily, weekly, monthly, quarterly? That would depend on what type of camera you would want. What kind of features would you want? Do you need Wi-Fi, extra optics, movable measurement tools? This will depend on your applications and who will use the camera. And lastly, who will use the camera? Will it be someone in reliability, or would it be someone who's an electrician just doing spot checks on electrical components? What type of reporting and trending will you do? That would depend on the type of camera you would want to archive and database the images that you would like to recall later. So after we got all these questions answered, here are the highlights of the FLIR cameras. The first camera line is the I-Series. It's what FLIR calls the spot gun replacement camera. And all FLIR cameras have radiometric JPEG image storage. This camera has a little micro SD card in it that will allow you to store images and comes with free software to create reports. But it's also fixed focus, or what we would call focus free, so it's very simple to use. It has a 2.8-inch color LCD and a max temperature rating of 482 degrees. It's very affordable, with pricing ranging from $1,195 to $1,995. If you need more performance, consider the FLIR E-Series. It has a larger screen, which is a touch screen that operates similar to an iPhone or an Android operating system. It has Wi-Fi for instant messaging to customers and your managers about problems that you found. It has a visual camera built in, picture-in-picture imaging modes and fusion modes. It has a laser pointer to indicate what's in the center of the image, with a video light to illuminate the visual camera or in dark areas. Has the ability to accept accessory lenses such as wide angle or telephoto, and temperature ranges up to 650 degrees C. This camera costs anywhere between $2,995 to $7,995. And lastly, for those that want the very best, FLIR offers its T-Series of high-performance cameras. And this is where ergonomics comes into play if someone's going to be using the camera a lot. These cameras also have high temperature up to 2,000 degrees C, have the capability to measure at long ranges with resolution of 640 by 480, which equates to 307,000 pixels, has remote control capability through the iPhone and Android apps, and is designed for constant outdoor use with an integrated eyepiece. These cameras range from $8,500 to about $26,000. That ends our presentation today. I have now listed the webinar schedule going forward, where we will deal with some of the more these topics a little bit more in depth. On November 5th at 2 p.m. Eastern, 11 a.m. Pacific, we will talk in depth about the spot IR thermometer versus the thermal imaging camera and see exactly why the IR thermometer does not measure as accurately as the thermal imaging camera. On February 4th at 2 p.m. Eastern, 11 p.m. Pacific, we will discuss what is thermal resolution and how does it impact temperature measurement using a camera. Basically, how far away can you measure something depends on the size of the target and the optics in your camera and the number of pixels in your camera. And our last presentation in this series is on May 6th. What is emissivity, reflectivity, and how they affect thermal temperature readings? This is the part where customers get to understand why shiny targets are hard to measure and how to compensate for them and how to correct for that and how to mitigate reflective issues. If you want to learn more about reflectivity and emissivity and some of these other topics, I encourage you to go to my training site at www.infraredtraining.com. It's the ITC, the Infrared Training Center, and there you'll see our course schedule for Level 1 through Level 3 certification. You will find this type of training invaluable if you take it. Lastly, if you have any questions, I encourage you to take down the data on this page right here. Colin Maxwell, who's the Transcat representative, can be reached at 800-854-8255. 4960 or his email address at sales@transcat.com. My contact information and my phone number is there as well. I can be reached at 866-379-4022. And my email address is my first name dot my last name at FLIR.com. I encourage you to send questions. We're here to help and help you understand the value of thermal imaging. Thank you very much for listening, and this is the end of the presentation. Thank you and goodbye.
Thank you, Ed. Well, that does conclude our time for today. Keep an eye out for invitations for some of those future webinars that Ed had discussed. You'll be able to sign up also on our website at transcat.com/webinars. If you do have any questions or would like to find out more about what was talked about today, you can reach out to Kyle Maxwell, as was previously stated, or you can call our general sales number at 800-828-1470, or you can visit us at transcat.com. I want to thank you today for joining us. We hope that the information was useful and applicable to your jobs, and we hope you have a good rest of your week. Thank you.